Right, so welcome to the third talk in this session on learning and tomography. Our speaker is Hyun-Soo Kim from UC Davis, and he will give a talk that is a merged talk about two papers on learning shallow circuits, and the title of the talk is Learning State Preparation Circuits.
Thank you, and good afternoon, everyone. As mentioned, this is a merged talk where we'll be presenting technically two works in the same talk, but both of them try to answer the same question, namely learning state preparation circuits. So let's get into it. The problem, as we say, is related to situations such as simulating quantum dynamics, which require efficient preparation of certain desired states. To even start a simulation, we probably want to prepare the states that start the simulation in the beginning. To do so, the question is, how do we learn the preparation circuit of some desired state? That's the very big question that we're trying to answer. Schematically, one can think of, say, some circuit you can implement to prepare the desired state psi. And so, given multiple copies of the desired state psi, prepared by some unknown circuit U, we want a circuit that prepares psi. That is the question. This question was actually somewhat addressed in a previous QIP talk just last year, actually, in 2024, which itself presented how to learn a preparation circuit for 1D two-dimensional states in spatial dimensions prepared by a shallow circuit, that is a circuit with constant depth specifically. So a natural extension of this that the authors considered is how can we improve this result? How can we go a bit further than the scope addressed in this work? So we want, essentially, an efficient method to learn preparation circuits that not only generalize to spatial dimensions, that is two or even larger, but perhaps also tests whether a circuit is indeed preparable by a shallow circuit specifically. So for instance, if there's a non-shallow preparation circuit required, is it able to know that? Of course, being ambitious, one can even consider a bonus of when we also learn for states not preparable by such circuits. So like I said, this is a merged talk presenting two different approaches. The first one by Zeph, Landau, and Yunchao, who unfortunately is not with us today on the conference, so instead I'm there on their behalf, as well as part two, which is called Locally Learning Extending Channels by Isaac Kim, my advisor, Daniel Ranard, and myself. So the first part is learning via undone local inversions. What does this mean? Well, a local inversion, we can consider it like this. Consider some geometrically local shallow circuit and some subsystem S, like so. Then, basically, considering the constant depth of that U and the constant size of that subsystem, one can essentially consider a local inversion, calling it V, which essentially resets the reduced density matrix of the subsystem, and that's how it is easy to find, because it's a constant size subsystem with a constant depth as the circuit underlying it. And if we take a look at inside this local inversion, that local inversion should cover the so-called pass light cone of a smaller subsystem of S under a geometrically local shallow circuit U, where the so-called pass light cone is essentially these green gates over here, the composition of the gates that are connected to that smaller subsystem S naught. So the idea is by using these local inversions, we should be able to reconstruct the pass light cone of every qubit that was in the preparation circuit. By doing so, we should be able to find a circuit that does indeed prepare the state that we desire. So the procedure that their method uses is as follows. Step one, apply a local inversion on some constant size subsystem A. So we essentially get the reset zeros back in subsystem A and some junk in the complement of that subsystem. Step two, you replace A with fresh qubits. That is, you basically apply a reset gate on the current state right now on A, and then basically supply them with fresh zeros. Note how this is a trivial operation, because we've already applied the local inversion that reset the state in the first place. But this trivial step is here for a reason, as we'll see. And then step three is to apply the inverse of that local inversion, i.e. undoing the local inversion that we just did. So it's a pretty simple procedure, and you may think why we do this. Well, first of all, as a result of this procedure, notice how the final state that we get after each step is unchanged. The desired state that we have remains unchanged once we undo the local inversion once again. And furthermore, thanks to the fact that we essentially supplied these fresh qubits over here, we are able to, by undoing the local inversion, learn the path light cone for the reduced density matrix on that constant size subsystem A0, which is slightly smaller than the original A. And note here again how the fresh qubits precisely provide the base of that light cone, so to speak. If we zoom in a little, you can visualize a bit like this, where at the zeros, at the A's, they all connect up to to form the path light cone of A0. So the idea is basically for each of these steps, you repeat it across multiple times. We repeat this, first of all, across non-overlapping constant size subsystems, such that, for instance, here's partition 1, 2, 3, 4, each of them with each of those steps we just discussed earlier. And then, for each of those, we will have some corresponding path light cones inside them for some smaller subsystems of each of those partitions. So, of course, when we do so, the path light cones of the entire state is not fully recovered yet because, well, very much we haven't addressed these subsystems at the moment, the ones that were kind of left out from A0, essentially. The idea is to cover these is pretty simple. You just repeat again, but now with a slightly different covering scheme. We repeat with more layers across sufficiently overlapping constant size subsystems this time to cover those original qubits that were missed in the first iteration. Doing so, we basically reconstruct the other remaining light cones to some degree, at least. Of course, this is a schematic. When you actually do this, you'll have to do this a bit more times in some particular covering scheme. But this is the idea. By sufficiently repeating it with more layers with sufficient overlaps, you should be able to cover the path light cone of every qubit, and perhaps including some of these so-called junk ancillaries. Because basically the path light cones, there will be some overlaps in them, but all we have to do once the light cones are recovered, you just discard them, essentially. So that's what we can do. And of course, once again, note how each path light cone correctly stops at the fresh qubits that were in step 2. So that trivial operation is not exactly trivial once we get this final result. So this very briefly, essentially, once again, the two questions that we wanted to answer in this method was to basically generalize how to learn these preparation circuits for spatial dimensions above 2, possibly, and also test whether a state is indeed preparable by a shallow circuit or not. This method is able to answer that question, where in the case of 2D plus lattices, you just simply have to take a geometry-based choice of subsystems that depends on what the lattice looks like, such that for the same layer, for each parallel iteration of the procedure, that we sufficiently non-overlap our choice of subsystems, versus for different layers, we sufficiently overlap them again. And there is a bit of in the actual paper by Zeph and Yunchao, they actually outline this a bit more in detail, of course. And then as for testing the depth of whether the circuit is shallow or not, if this construction succeeds, well, by explicitly constructing such a shallow depth circuit, we show that indeed the preparation circuit should be shallow. Versus if it fails, then there is actually a rigorous guarantee inside the paper itself that indeed confirms that the shallow circuits cannot prepare this state. So basically by preparing this, you were able to say that it succeeds and thus the preparation circuit should be shallow, otherwise it's not. So the first result, the first approach essentially is an efficient method of learning preparation circuits for such states, such desired states, with a shallow depth unitary that prepares them. That's the promise that we have. And also, it also tests whether that promise has been kept or not, essentially, such that psi is either indeed a shallow preparation circuit or it is not. So for details, again, please feel free to consult the manuscript by Zeph and Yunchao. Again, they are not with us here today, but hopefully I was able to relay at least the basic idea. Now, the second part is basically the one by Isaac and Daniel and myself, where basically we learn by a slightly different method, where previously we talked about how to do things with local inversions. In particular, consider the fact that the first method basically took these constant subsystems, partitioned the system up, and then learned the path light codes over those. We take a slightly similar approach, but instead of learning via local inversions, we learn via something we call extending channels. What is an extending channel in this case? The name is quite literal, in that we first start with our desired prepared state. We then partition and learn the reduced density matrices on disjoint constant size subsystems of these local subsystems. So these blue patches over here are supposed to represent the local subsystems that were learned by, say, state tomography. Then, step 2, we learn and apply a so-called locally extending channel phi naught and connect up the disjointed subsystems. Previously, we had these constant size subsystems that were not connected to each other. By applying the channel, you should be able to, we aim to essentially connect up those states that we have. And then we repeat until psi is indeed fully reconstructed. So unlike the local inversion, where you find like the actual inversions, the local inversions for each patch, so to speak, here we actually try to connect up the patches by applying some channel for each step. Well, what exactly are these things, though? So local extendability, you can consider it as this. Basically focus on this, say, constant size local connecting subsystem that we just described earlier, and let's try to like actually think what extendability is in this case. The idea is, we desire the following. We desire, basically, first of all, let's say considering like say some setup like this, where we have the known regions that we just described as blue, as B, and the connecting part of the subsystem as C, highlighted in red or pink, as you can see here. The idea is, for the remaining purifying system, we want to leave that untouched. We don't want to change anything with that, otherwise it ruins the whole purpose of trying to find an efficient algorithm. What we want to do is then apply a channel such that it starts from the reduced density matrix of BE, or rather we start from the space of it, and then it extends over to the space of BC, like so. So basically we start from like the sides and then connect up to C over here. This is how we motivate the definition of a locally extendable state, where a state BCDE, the density matrix BCDE, is called locally extendable if there exists a channel from BE to BC, such that when you apply this operation, identity on the purifying and applying the extending channel, we recover from the reduced density matrix of ABE to ABC, like so. This is our definition. Well, how do we then, as a guiding example of such an extending channel, consider the following. Our good old friend, the product state, where across this, like say, as something equivalent to this choice of partitions, each subsystem has a reduced density matrix over it. The idea is then, this extending channel is achieved by, well, the construction here is actually quite simple, because thanks to the fact that these are all this is a whole product state, and thus each of the subsystems are not correlated with each other, you simply append the reduced density matrix on C, and then trace out the subsystem E, plain and simple, in the case of the product state. So indeed, a product state is indeed a locally extendable state, as we described, including the good old all-zero state, as was pretty prevalent in our pictures of preparing circuits up until now. So the key result, at least concerning this partition, or this set of subsystems over here, is that there is a set of conditions that verifies whether a state is extendable from BE to BC, and there is also an efficient algorithm that learns the extending channel of BE to BC, like so. So if you're given like basically any state, if we choose this to be our distribution of partitions, there is a conditions to which that indeed the state is extendable over this, as well as learn the actual channel that does that job. Now, consider the effect of the shallow circuits on a product state. Again, consider our problem in that it is multiple copies of psi prepared by unknown circuit U. We want to prepare psi with some circuit. In particular, for shallow preparation circuits, notice how the psi state over here, the desired state, is essentially the all-zero state with a shallow depth unitary applied to it in the case of a shallow preparation circuit. So the question then is, if U is shallow, should that psi state should also be extendable? Now, notice the following. Notice how the product state, when we first discussed it, that was extendable due to the fact that there was no real correlation between the subsystems. Because there's no correlation, so we just append and trace out, essentially. So then if we apply a shallow unitary onto the product state, consider the effect of that unitary as we can see via the light cones of each subsystem in our product state. When we do so, here's, say, C and A and the rest of the system as like an example. So the light cone of C and A like this. When you consider that, as long as the intermediate region, BDE, is sufficiently thick, A and C will still not be correlated because the light cones don't even reach that far. As long as the system in between them is of sufficient thickness, the shallow depth, the fact that U is of shallow depth, should guarantee that the correlation does not go over to the other side. As for adjacent subsystems, there will be some correlation length that's non-zero, but it should basically still remain a constant from the fact that it is indeed, from the fact that the depth of the circuit is shallow, like so. So then, then we may suspect that psi is indeed also an extendable state, perhaps for some partition choice that is fattened or thinned by the order of the depth, the constant depth of the circuit, because again, correlation length can only go that far. So the key result, another key result essentially that we have for this partition at least, is that if a state is extendable from BE to BC, it is also extendable under a shallow U for a slightly different topologically equivalent partition choice. And the corollary of this then is, well, since for any shallow circuit U this should work, any state of this form of shallow U should be extendable, like so. So basically we not only discuss the product states, but basically all states that are connected via a shallow depth unitary to it as well. So then the procedure is simply quite this. You take local state tomography to learn the constant size subsystems, learn the extending maps that connect them up together, estimate an approximation error, and then if that approximation error is lower than the target error, then the circuit is built. Otherwise, we can either try expanding the sizes of these local subsystems at the beginning, or we just declare that the algorithm has failed. The construction fails in this case. So as you can see, basically we do step one, just like we did. Step two, we basically learn the extending channels according to that partition choice. And then step three is a special case of the exact same learning choice we just discussed, only when DE is just merged with B, essentially. So it's just another part of the step, the procedure. So once again, the question that we considered previously was whether basically this problem is generalizable to dimensions 2 or above and tests whether a state is preparable by some shallow circuit. So all we have to do for 2 plus lattices is just repeat this for analogous K-cells rather than the two-dimensional example that we discussed. And just like the previous first method, if the construction succeeds, we indeed have a shallow circuit. Otherwise, it fails, like so. We have some more rigorous arguments about this as well. Now, real quickly, there is also the bonus problem that we consider in the second approach of learning states not preparable by shallow circuits. For instance, one can consider certain topologically ordered states where, say, if sigma over here is, as an example, maybe the Tor-occurred ground state on a disk, or maybe it's like some string net model ground state, something like that. What we want then is basically the preparation of such sigma and the preparation of, with such sigma, the psi state over here, which also is a shallow depth unitary applied onto that topologically ordered state. Then we have a slightly different issue coming up, where in the case of the original partition choice that we had, there is no such shallow unitary. If there is no such shallow unitary, then this is not, extendability from BE to BC does not hold in this particular partition case. However, if you slightly change the partition and change it into this essentially, there is actually a set of conditions for which a set with a state with no shallow U, such that this is the case, is actually extendable from BE to BC. And if those conditions do work, as we confirm in our paper for these two examples, and according to a previous known result, the key result is that if a state is extendable from B to BC, it also is extendable again under a shallow U. So basically, it's very similar to the original, or the first version of applying a shallow U, but with a different partition shape. So once again, even if it's not the all zeros or even a product state that's as sigma, we are still able to maintain, extendability remains under a shallow depth unitary for these kind of states as well. So the procedure is once again to simply, instead of now disjoints parallel patches, you just take one patch essentially, learn it, learn the extending channel according to this partition choice, as we just discussed. Keep on going, patch up according to, once again, this one-sided partition that we have over here, until we essentially recover the entire desired global state with perhaps some junk qubits in the middle, because each step is a channel. So in order to construct the full circuit at the end, we would probably need some dilate to a unitary. So to summarize, the second part is an efficient method to learn preparation circuits for states of this form, where sigma is either a product state, which works for both of the two partitions that we just discussed, and also an extendable long-range entangled state, or a topologically ordered state, which succeeds for partition 1, but fails for succeeds for partition 2, but fails for partition 1. In fact, that failure of the partition 1 for such states is indeed a test, provides a test for the shallow depth of the preparation circuit, because if it succeeds for partition 1, then indeed it's a shallow depth. If it isn't, it is not, like so. Once again, for some more like rigorous and technical details, please refer to this paper. And yeah, we are delighted to have presented our results to you guys. Thank you very much.
Thank you for the very nice talk. I have a very simple question. So if you don't know the structure of this circuit, like I just give you unknown quantum state, and I don't tell you which qubits are close and which qubits are far away. Are these tasks still simple, or it becomes very hard?
So for concreteness, in our case, we focus on geometrically local circuits.
Yes.
Yeah. So the promise is that for now it's geometrically local, and
yes. I mean, like maybe you don't know the geometry. I just tell you it is geometrically local, but you don't know the geometry.
Right.
In this case, do you think these tasks are simple or
not? It shouldn't. I don't think it'll matter too much. I think. Basically, if you're referring to the geometry, do you mean the geometry of the circuit? Is that it, or?
Yes. So like I use a shallow circuit to prepare a state, and I somehow like randomly permute all these qubits and then pass a state to you. So you don't know which qubits are close and which qubits are far away. In this case, do you think?
I see. Oh, I see. Concretely, we focus on specifically lattices.
Yes.
So basically, the qubits are they have a notion of locality to them.
Yes.
So if that's not the case, then I don't know how this will extend. Yeah.
Okay. Thank you.
Hi. I had a question, which is, so it seems like because you're doing this dilatation channels, this might also work for shallow depth, like CPTP maps, if I do some measurement and feed forward. Is this correct? And the second question I had was, what is a setting in which this learning algorithm is useful? Like, what's an application?
Would you repeat the second question?
What would be like a setting in which you would use this algorithm? Like, what's an application of
I see. So to answer the first question, possibly. I don't think we've really considered it for like CPTP maps in general yet, but yeah, like at least the second construction is using channels and not like unitary local inversion. So we think there might be, but we don't have any like results on that yet. So there's that. And then for the second one, let's see. Basically, the idea is, if you have, we're trying to be we're pretty generic as we try to be. So that it's as flexible as it can be in terms of applications. So any situation where you have some like lattice structure, you have like your qubits like distributed on them, and as long as that lattice is pretty like sufficiently large, and our subsystem choices aren't also too small are relatively large compared to the circuit depth, then this algorithm should basically work for any like state that meets the conditions, essentially.
As in, when would you use it? Like, I know when it works, but.
Well, I guess this is supposed to present like an explicit way to prepare like some desired state. So, for instance, like again in terms of like quantum simulations, for instance, if you had some like state that you already have and you have multiple copies of it, but then for some experiment you say want to prepare it again, then this is like something you can use.
Thank you.
Hello, thank you for the very nice talk. So my question will be a bit more technical. You didn't give any technical details, but so seems like from the diagrams, like the gates that you have on that circuit, I mean, they're unitary because like we are assuming that it's in a quantum computer, but it seems like the assumptions that you have, or like the light cone stuff, basically do not assume that doesn't require them to be unitary. I just wanted to ask, like, you have some proofs for if this doesn't work, then there's no shallow circuits that will prepare a state. Like, is that proof, like, does it require these gates to be unitary, or can it be extended to non-unitary cases as well? Like, as in, like, imaginary time evolution stuff.
Let's see. It's if you're talking about the unknown preparation circuit, then we consider specifically for unitary circuits specifically. Yeah. Does that answer your question, or?
Yeah. I just wanted to ask, like, about. Okay, you considered it, but like in the proof, like, do you think the proof can be extended to non-unitary circuits as well? That's basically the question.
Let's see. So at least one of our key results was the fact that if a state is extendable for these partitions, then after a shallow depth unitary, it will remain extendable. That we don't have like a proof for non-unitary cases in that case. So if like you apply some like CPTP map, is it still remain extendable? Like we don't have a proof for that. So for unitary specifically. Yeah.
Okay, thank you so much.
Thanks for the talk. Does this work for fermion systems? You know, I can think it probably won't either in first or second quantization because, you know, things seem to be non-local, but, you know, I don't know. I wanted to
Right.
see some
I don't really know the answer. I don't know the actual answer to that question, but we work with qubits throughout this entire thing. So perhaps like if we define like some equivalent notion of extendability for fermionic systems, then maybe. But I don't think it works, at least from here. Yeah.
Hi. So in the topological phases setting, does your learning algorithm need to have knowledge of the initial state sigma?
Yes, or rather, if you're given the state, you can actually check whether it is extendable under the conditions that we have. So if once it is checked to be extendable, then we can apply the algorithm. Otherwise, it's just a state that cannot be treated by the algorithm.
So you can also distinguish between, say, a trivial phase and, say, topological.
Correct, yes.
All right. Thank you again for the great talk.